Karl is our first speaker. Please go ahead. Thank you.
Okay, thank you, and thanks for the invitation to this conference. It's great. Is it on?
Yeah, now you're on, I think.
I hear it.
Yeah.
Okay. So today I'm going to talk about preconditioning for sparse inference. And I apologize for any notational confusion. This is the notation that I'm going to use in the talk, where X is the design matrix, Y is the outcome. So you measure both. We want to estimate beta star, and it's corrupted by noise. And this work is joint with Jinsu Jia. When physical constraints restrict the way that you can measure the system, or when this design matrix is observed, for example, in fMRI or in GWAS, we often fail to satisfy the restricted isometry property or any other of the conditions for consistency. And so I'm going to use this as a catch-all term for things like the irrepresentable condition and so on, restricted eigenvalue condition. And preconditioning can sometimes correct for the problems. But before we talk about preconditioning, I want to talk about a teaser that I think is really surprising, and it's actually how we started to think about preconditioning for inference. And it's not going to be immediately clear how it relates, so you don't need to think about preconditioning for the next few slides. In classical statistics, when you have lots of rows and a few columns, so in a low-dimensional setting, and you want to estimate beta, the standard ordinary least squares estimator is the best linear unbiased estimator. But, when your noise terms are IID. But if there's some errors that are not ID, so either heteroscedastic or correlated with a covariance matrix sigma, and you know sigma, you can easily correct for this. You just left multiply everything by sigma to the -1/2, and then you run OLS on the whitened version of the data. And this gets you the best linear unbiased estimator. So now that was in the classical setting. In the high dimensional or in the sparse setting, this framework could easily be adapted, and you could run the lasso instead of OLS on the transform data. And if your error terms are Gaussian, but not IID, this gives the penalized MLE for the errors. So here's a quick simulation. We're going to compare GLS plus the lasso. This means the transformed data with the lasso, or just no transformation. We're going to run the lasso on the heteroscedastic data. So in the simulation, P is 1,000, N is 200, 20 relevant predictors, and X just contains IID Gaussian elements. We're going to choose a tuning parameter with the oracle. And the important part here is that we're going to get heteroscedastic error terms. So you need to somehow determine what the standard deviations are, and so just sample from a gamma. And on the x-axis, the noise is going to become more and more heteroscedastic as you go off to the right. And the y-axis measures the error in this way. So off at the lower left-hand corner, this is a homoscedastic model, and these two lines, they overlap. And as you move to the right, they diverge. Okay? And on top, there's this null estimate, which is estimate beta hat equals 0. And what you see is that one of them is whitened and one of them is not. One of them converges to the null estimate, meaning that it's not doing anything. It's just telling you to estimate a vector of zeros, while the other one doesn't really seem to be too perturbed by the heteroscedasticity. And so the first time I looked at this, I thought there might be an error in my code. I thought, okay, so I must have just flipped this around. The GLS plus lasso must be on the bottom, and the heteroscedasticity must be making this thing horrible if you don't correct for it. But in fact, it's the opposite. So whitening worsens estimation. So you actually don't want to do the penalized MLE. You want to just run with the standard lasso. And I thought this was really surprising. So left multiplying by sigma to the -1/2. To whiten the noise, it made estimation worse. So why is that happening? And if we can understand that, maybe there are other matrices that will improve estimation. And when we first thought of this, that was kind of like a distant thing. We had no idea. It was kind of a conjecture. So next I want to talk about the lasso and the conditions for consistency. This might be a lot of review for people. And so the current literature has explored several of these conditions. So there's RIP, null space property, restricted eigenvalue, irrepresentable condition, mutual coherence, and on and on. There's a lot of these things, and they control different types of consistency for the lasso. And all of these conditions somehow measure the correlation between the columns of X in various ways. And so the first three are kind of similar in some respects. I'm going to work with the fourth one, the irrepresentable condition, because it's easiest to compute. It's not like an NP-hard problem to compute it. So we can compute this in simulation. And so just a reminder what the irrepresentable condition is. It's to select the right sign pattern, or if you want the right support, to get the right support. And this is the form of the irrepresentable condition. We want this thing down at the bottom. We'll call this function IC of X. We want this to be less than 1. Okay? And so if you're not familiar with this, what you're trying to do is basically predict the irrelevant columns. So the columns that, if you know the true pattern, you want to predict the irrelevant columns with the true columns. And if you can do that, then that's bad, right? That means that they're too correlated and you're not going to get the right support. And it's sufficient and it's nearly necessary. Okay, so we have less than 1 minus eta for some slack term. If you go over 1, it's no longer consistent. And so here, again, another simulation to just show how sensitive this condition is to a little bit of correlation. The rows of the design matrix are now IID, the rows, but the columns are not independent. There's a little bit of correlation. So starting off at the left, there's 0, so they're independent. And then as you go one tick over, it's 0.01. So they're just a little bit correlated. And the vertical axis is the value of the IC, right? And we want this to be less than that solid line at 1. And you can see that the red line quickly breaks through the line of 1, meaning that for just 0.08 in the correlation, you are no longer sign consistent. So if we're in the setting where we don't get to design the design matrix, this would be like a dream in most observational studies to have correlation 0.08, right? Not 0.8, but 0.08. It's very little, and you're already breaking the irrepresentable condition. We'll come back to the black line later, but that's where we want to go. So I'm not the first to realize that this is a tough condition, and other people have proposed other ways of addressing this. These techniques aim at the penalty term, okay? And so they think the L1 penalty is the problem, and so they either make it non-convex or they do a two-step procedure as in the adaptive lasso. And today we're going to take a different approach where we actually look at the loss function, and we're going to change the loss function instead of the penalty term. The L2 error term is we're going to change that. So for the rest of the talk here, we're going to talk about preconditioning, and I'm going to introduce what that is. So some people are probably very familiar with that, much more than I am, but we'll then talk how it relates to what we want to do. And then we'll give low dimensional and high dimensional. We'll talk about both cases. So preconditioning, it's a tool from numerical linear algebra where you want to solve a system of linear equations. And here the notation is backwards from what I've been talking about so far, but you have AX equals B, where A is the design matrix and B is the outcome you want to solve for X. And it's a game of algorithmic speed, right? And most solvers depend on the condition number of A, that is the maximum eigenvalue of A divided by the smallest eigenvalue of A. And if this ratio is large, you just take a long time to converge because it's ill-conditioned. So what preconditioning says is that you left multiply by some matrix T, and T is designed so that the condition number of TA is less than the condition number of A. Okay, so in some sense, a best preconditioner would be A inverse, right? That completely solves the system. But you go too far. You have to trade off the computational time, right? And computing A inverse just takes too long. So usually you do something weaker than that. So I'm a statistician, so how do we think about this in terms of statistical ideas? So imagine that A is a data matrix, and you want to look at the principal components. The first thing you would do if you did PCA is look at the eigenvalues, right? And if you have a few eigenvalues that stick out, that suggests that the first few eigenvectors are picking up a lot of the information. They're discovering some correlated structure in A. And at the same time, what that suggests, if you have these large eigenvalues, it means that the system is ill-conditioned, okay? So what's happening here is that the condition number very much relates to how correlated the columns are. And when the columns are more correlated, the condition number is bad. So another way of thinking about preconditioning is that it's just decorrelating the columns. Now, if we think about the conditions for consistency, all of these things somehow depend on the correlation between the columns. And so if we can decorrelate the columns, then we can potentially circumvent these conditions, right? Where the original design matrix that we observed, X, does not sample these conditions, maybe after preconditioning it does. that was review for you. I apologize. Now I'll get to some new stuff with how we precondition the lasso. So take the SVD of the design matrix, and if you're thinking about a MATLAB code, it's the economical SVD. So I've drawn kind of a picture of what this thing looks like. And we're going to talk about the puffer transformation, which you take the UD inverse U transpose, right? It's just defined from the matrices from the SVD. And the reason that this is an interesting thing is that if you look at f times x, what it does is it sets all of the singular values to 1. Okay, so x might have very widely varying or singular values, but after preconditioning, they're all set to 1. So instead of running the lasso on x and y, right, from our original model, you can run the lasso on fx and fy. Oftentimes when I've given this talk or I've tried to describe this to people, at the end of the talk they say, well, you're mixing up the betas when you do the preconditioning. You're not estimating the same beta. But it's important to note that we're not mixing up the columns with the preconditioning. We're mixing up the rows. Okay, so when you precondition, before preconditioning, each row might correspond to a person or something, some observation. But after preconditioning, you're mixing up the observations, right? It's no longer, one row does not mean anything in particular. But the columns still do, right? The beta star does not change, right? So if you run the lasso on fx and fy, you're still estimating the same beta. Beta hat is going to be different, but you're still estimating the same beta. So it's easiest to state the results for low dimensions, that is when you have more rows than columns. And what happens after this preconditioning is that you have orthogonal columns. Okay, and this trivially satisfies all of these conditions for consistency. And so here's a theorem. It just says it's a sign consistency theorem. And the important part of this theorem is that it does not have an irrepresentable condition. Okay, so previous theorems that just use the lasso out of the box, you would need something like an irrepresentable condition. But instead, what we have is a lower bound on the spectrum of x. So let's look at that. That's kind of what it's swapped out with. So when you left multiply this regression equation, you left multiply y and x beta and also epsilon. And that's kind of the bad news, is that you have to multiply epsilon at the same time. And so your preconditioned errors are no longer IID if you started off with something that was IID. And so if f has, say, a big spectral norm, this can really blow up your noise term. It's bad news. And so in our proof technique, you need to bound the spectral norm. And the spectral norm of the preconditioner is the smallest squared singular value of x. Okay, so is this the punchline? Is this a bad news punchline? That when the columns of x are correlated, this is when we actually want to precondition. But then x has a small singular value, and f amplifies the errors. It's not the end of the story. So there's a simple fix, actually. You can replace the largest singular values of f with something else. You can either throw them away, you can set them equal to 0, anything to somehow bound it. What these correspond to are the smallest singular values. They correspond to the directions that have the smallest singular value in x. And so if you just throw these away, you're just throwing out your weakest directions that you're sensing. And so it doesn't feel so bad to throw those things out. If that feels bad, you can just bound them, anything else. And so somehow getting rid of these things, it's like discarding rows, right? It's like discarding samples, but they're not good samples to begin with. So it's an easy fix. Okay, so in the high dimensional setting, it's more difficult to state the results. Because in the low dimensional setting, you got perfectly orthogonal columns, but that's just linear algebraic impossibility in this setting, right? When you have more columns than rows, they can't be perfectly orthogonal. Excuse me, so what can we say? Well, it does have orthogonal rows. And I think it was Amit yesterday actually cited this same exact paper from 1955. I think it was for a different result, but maybe I missed something in his talk. That Fan and Hoffman showed that for any unitarily invariant norm, fx is the projection of x onto the Stiefel manifold. And this is the set of n by p orthonormal matrices. Right, so they originally thought about the transpose probably, but it's a short fat matrix that has orthogonal rows, orthonormal rows. And there's an existing literature that suggests if you have orthogonal rows, maybe orthogonal, drawn from a nice distribution, then a design matrix is well conditioned in terms of RIP. And so I'm sure that there are other publications that I've left out here, but these were the first 4 that came to mind. So we don't have orthogonal columns, we have orthogonal rows, but there's a more involved theory to look at that. For just a quick idea of what's going on, here's another simulation where you take the rows of X are Gaussian, IID Gaussian, and the columns have correlation 0.9. Okay, so this bump over off to the right is the a histogram of the pairwise correlations in the design matrix before preconditioning. And then you see this other bump way off to the left, and this is the histogram of pairwise correlations after preconditioning. Okay, so this is something that's hugely correlated, but it's correlated in a way that's totally trivial to handle with preconditioning. Right? If in the low-dimensional setting, this left bump would be a point mass at 0. Here it's just spread around 0. And so here's, again, the rest of this simulation. Before I only went up to 0.1. This goes all the way up to 0.9. And you see that before preconditioning, the design matrix has an irrepresentable condition that exceeds 1. Right? So you're not sign consistent. After preconditioning, you're well below this line. And it's important that not only are you below it, but there's a good distance below that line, because as you get closer to the line, the results become very sensitive to that, and so you need more samples. Okay, so how am I doing on time? Okay, I don't want to buy everybody lunch. Okay, so in the simulation, n is 250, and there's 200 relevant columns. And P is going to grow on the horizontal axis from 32, so a low-dimensional setting, to a very high-dimensional setting, 32,000. And the rows of X are IID Gaussian, and we're going to have increasing levels of correlation. Okay, so I'm going to flash forward it so we can look at this. So going down, in the top row, there's only a little bit of correlation, then a moderate level of correlation, then a high level of correlation. Okay, and now the columns measure 3 different types of error. In the first column, it plots the number of false negatives. In the second column, it's the number of false positives. And in the third column, it's the L2 error. And the tuning parameter, if anybody's interested in how I selected the tuning parameter, we should talk about that after the fact, because it's not trivial. Okay, so the preconditioned lasso is in black. And I think that there's a few key pieces. First of all, in the lower left-hand corner, this is the highest correlation, and it's the number of false negatives. And the black line is basically staying at 0 all the way out to 32,000. Everything else shoots up, and you get a whole bunch of false negatives right away. At the same time, the number of false positives in the next column over is still better than everyone else. Okay, and the L2 error demonstrates this. Okay, so here's, I had this weird way of choosing lambda. So here's, you just take the first 10 predicted coefficients. You don't actually look at the whole path and choose a good lambda. You just take the first 10 predictors. The important thing to note here is that there's this weird little bump in the black line around 250. And remember, n is 250. And what this is showing, I didn't do the easy fix for the preconditioner. And so when n and p are kind of moderately close to each other, you have these random matrix results which suggest that you get really small singular values in the design matrix, and so then it just blows up, right? And so you need to do something about that. I didn't do it in the simulation here, and there's a price to pay for that. Okay. So let's recap and open problems. Okay, so we talked about GLS at the beginning. That was kind of the teaser to start talking about it. And what it's actually doing is preconditioning. It's doing the same thing. It's left multiplying by this matrix. The thing is that it fixes the error distribution and makes the design matrix worse. Right? And it turns out that the design matrix is much more of a problem in these settings than any sort of error distribution, because you're just going to bound the spectral norm. This particular type of noise might not matter nearly as much as the conditioning of the design matrix. Excuse me. Okay, so I think that there are lots of open problems with this. Because this is done after sampling, right? So you have collected your data and you realize that there's some correlation that you're worried about. This is quite easy to apply to some data set that you have lying around. It's not in how you design the experiment. So real examples, I think, are really needed to demonstrate or to examine if this is actually an issue, right? I suspect that it is, but we're still working on some examples to show that it actually helps. Also, I think that there's questions in non-regression settings, so sparse inverse covariance estimation. There's something like the irrepresentable condition that pops up. How would you precondition there? In fitting the logistic regression, you're left multiplying with iteratively reweighted least squares. This is one data technique that's similar to many others in that they left multiply the regression equation by some matrix. And you don't really think about it in that way, but that's what it's doing. Also, the bootstrap does this in something statisticians call the generalized lasso. And so these things, they can change the conditioning. So if you're not careful, you can be trying to help. There's a good reason that you're helping, but you're actually making things worse. Also, I didn't explore at all how we could make fitting faster. Traditionally, preconditioning has been used to make faster algorithms. And it seems plausible that that should be the same case here. But I was just interested in statistical estimation. So I think that there's a lot open to think about there. OK, so the key points. Lasso fails when the columns of X are even weakly correlated. If they're moderately or highly correlated, forget about it. But even weakly correlated, it's bad. And preconditioning can often fix this problem. But it gives the error terms a strange distribution in the process. But you have to do this quick and easy fix of thresholding the spectral norm of F. And in simulations, this performs really well. And I think that there's several open problems. Thank you.
So the opposite also works. He gave us a great talk on time, so he's going to get free dinner as a reward. And you know, it has the risk to have to pay for that dinner in that sense. But we have time for questions. He was so kind to be on time. Also clear? Okay, so I'm going to ask you a question related to your open. So we heard in the morning some other model, let's say Novak's model of the group lasso plus regular lasso. So you think that you should do preconditioning for other terms beyond lasso?
I think that it's interesting. Right now, our preconditioner is in no way optimized for RIP or anything. It's a very blunt hammer that we're just kind of like hitting the design matrix with. And so it could just work out of the box. But I think it's an interesting question, is would you do anything differently if you knew that there was some group structure and so you were interested in something else than these conditions? I don't know. Yeah.
So you don't know for which class of penalties your preconditioning could be?
It's such a blunt tool that I think that you have to go back and just say, if you have orthogonal columns, or excuse me, orthogonal rows, do these types of sampling designs, do these types of designs satisfy those conditions? And that would be the way to proceed. But in no way was this preconditioner ever designed to drill in on RIP or anything, or a presentable condition. Yeah. Thanks.
The question was on if there is any implicit assumption on IID noise.
So in the theorems that we proved, we did assume that there was IID noise, but then you corrupt it, and so you no longer have it. If you initially started with something that was not IID noise, then you would just need to have a different spectral bound for the error term, and it would hopefully slip in there quite easily. I don't know. And I think maybe what you're alluding to is that there's this interesting question. So now if we also want to do something like GLS, if we know that we're starting off with something that's bad in the error term, can we simultaneously design something that kind of helps in that direction while also helping on the design matrix? And I think that's a very interesting question. I don't know.